All right, here we go. Welcome to Unit 14, Gas Laws. Our first lesson, 14.1, deals with Avogadro's law and gas stoichiometry. So a little bit about gases, the nature of gases. The particles of gas are usually molecules or atoms. This is important to keep in mind. Molecules means that they are covalently bonded together. So we're talking about two non-metals bonded together, or plain old atoms. Hopefully you're familiar with, on the periodic table, which elements are gases, which ones are liquids and solids. So the particles in a gas are considered to be small, hard spheres. You can picture them almost like very tiny billiard balls with an insignificant volume. So they're so small we don't even consider their volume. The motion of these particles, as is kind of illustrated here, is random, rapid, and constant. They never stop. They might slow down, but they never stop, and they're always going just in random direction, bouncing walls, bouncing off each other, changing direction. When they do, they collide. So it's random, constant, and rapid. All collisions, so you see when the gas particles in the illustration run into each other, all collisions are expected to be what we call perfectly elastic. And elastic means that there's no energy lost in the system. So there's no sound made, no heat lost. They're completely elastic. The energy that one of these little molecules or atoms has is going to be transferred perfectly to another atom or molecule. Temperature. When we talk about temperature, we're looking at the average kinetic energy of a gas particle. How much energy it has or how fast it's moving. So a cold gas is going to be moving a lot slower than a fast gas. And that's what we have illustrated here. These particles are moving very fast. That's why they have these long lines. And these particles are moving very slow, which is why they have such short lines. Now notice, not all particles are moving at the same speed. Some of these guys have really, really short arrows, some have slightly longer arrows. And the same is true of our fast gases, and the same is true of the picture up here as well. We've got some molecules moving really, really fast, and others just kind of motorboating around. So it's an average speed, an average amount of energy. The average amount of energy. So some are moving slow, some are moving fast, but temperature deals with the average motion. We saw this briefly last chapter, STP, which stands for Standard Temperature and Pressure. Now these are values you're going to have to memorize. If you didn't last chapter, that's fine, you got away with it. This chapter you need to know them. Standard temperature is either 0 degrees Celsius or 273 Kelvin. This capital K here stands for Kelvin. Note, there's no degree sign for a Kelvin reading. So here are some temperatures. Fahrenheit, obviously the one we're familiar with. We don't work with much in science, so you don't have to worry about these 212 degrees or 32 degrees. Really only in America that we work with that, and in America it's not at science. On the Celsius scale, water freezes at 0 degrees Celsius. So 0 degrees Celsius is equivalent to 32 degrees Fahrenheit. Water boils at 100 degrees Celsius. So 100 degrees Celsius is equivalent to 212 degrees Fahrenheit. The Kelvin scale is a little bit different. So you'll notice here on the Celsius scale, we have an absolute zero, is what we call it, a lowest possible temperature. On Celsius, the lowest possible temperature in the universe is negative 273.15 degrees Celsius. On the Kelvin scale, we've eliminated the negative temperature. Sometimes we want to do calculations and we don't want that negative value. So the Kelvin scale is the same as the Celsius scale, except it starts at absolute zero. The lowest possible temperature is 0 on the Kelvin scale, which means water freezes at 273.15 Kelvin and water boils at 273.15 Kelvin. Gives us a pretty easy conversion. Kelvin is equal to degrees Celsius, whatever degrees Celsius you have, plus 273.15. So room temperature is at 23 degrees Celsius. What temperature is this in Kelvin? Well, 273 plus 23 degrees Celsius tells you you have 296 Kelvin. Again, notice there's no degree sign. That would cost you a quarter or a half a point because it's not the correct unit. So watch that degree sign. It's only on Celsius, not on Kelvin. You can memorize how to do this conversion, that 273. Most of our gas laws only work when you're working with Kelvin. So be very comfortable with being able to convert Celsius to Kelvin. Standard pressures are 1 atmosphere, or 101.3 kilopascals, or 760 millimeters mercury. These are also standard values, and you're going to need to have them memorized also. So if you haven't yet, we talked about them briefly last chapter, but if you haven't yet, you're going to want to make sure you take a look at and memorize these values as well: standard pressure and standard temperature. Here's some examples of problems where you'd need to have your conversions memorized. So Denver has a pressure of about 95 kilopascals. What is the pressure in atmospheres and in millimeters mercury in Denver? Okay, well, we're looking for atmosphere. Question mark atmosphere is equal to 95 kilopascals. Now, we know that 101.3 kilopascals equals 1 atmosphere. So we can get our kilopascals to cancel out. We can do our math. We can see that it's 0.93 of an atmosphere. So Denver, the mile-high city, is a little bit higher than the rest of the country. And therefore, they have a little less air on top of them. So they have a little less pressure exerted down on them. They don't have 1 full atmosphere. All right, second part of the question, how about millimeters mercury? Again, we're starting with 95 kilopascals. We know that it's 101.3 kilopascals in 760 millimeters mercury. So we're going to crunch the numbers, and we think that the pressure in Denver would be about 710 millimeters mercury. Next up, we have Avogadro's law. Yes, Avogadro is in the number 6.022 times 10 to the 23rd. To tell you the truth, he did not come up with that number. He didn't work with that number much at all, actually. That number was named after him because of his work with gases. He was a lot more of a gas law guy than he was a sheer number guy. So what Avogadro found is that at STP, so only when you are at 0 degrees Celsius and 1 atmosphere, when you have 22.4 liters of a gas, it has exactly 1 mole of gas particles, 6.02 times 10 to the 23rd particles of gas. It doesn't matter what gas it is. Here we have neon, oxygen, carbon dioxide. Each of them has a volume of 22.4 liters, which means each of them has 1 mole of gas. And it doesn't matter that neon is smaller than oxygen, which is smaller than carbon dioxide. At STP, 22.4 liters of any gas has 1 mole. So some practice problems here. If we have 3.2 times 10 to the negative 3rd moles of carbon dioxide, we would expect it to take up a volume of 0.0717 liters. Again, we're looking at 3.20 times 10 to the negative 3rd moles We know it's 1 mole per 22.4 liters. Do the same thing for nitrogen. If we have 3.7 moles of nitrogen, 1 mole of nitrogen will occupy a volume of 22.4 liters at STP, which gives you a final volume of 82.9 liters of nitrogen. And finally, 0.96 moles of methane, CH4. The same is true. It's a gas, so at STP, 1 mole of that gas will occupy 22.4 liters. We'd expect 0.96 moles of methane to occupy 21.5 liters. More importantly, at STP, how many moles are in these volumes of gases? So 6.72 liters, we can work backwards. And now we've got liters on the bottom. We know that 22.4 liters equals 1 mole. We crunch the numbers, we get 0.3 moles of SO2. Let's say we had 0.880 liters of helium. Well, we'd expect that to be 0.0393 moles of helium. And finally, 1 times 10 to the third, that's 1,000 liters. C2H6, that's ethane. 22.4 liters per mole, or 1 mole per 22.4 liters. Lets us know that we have 44.6 moles of ethane. All right, now, more importantly, gas stoichiometry. Knowing the exact volume that a gas will occupy allows us to go from volume of gas to moles of gas, which allows us to go to stoichiometry. Anytime we have moles, we can use stoichiometry. So our coefficients can relate moles to moles of one another. But since we know that moles equals liters, we can say liters equal liters as well. So 2 liters of hydrogen gas will react with 1 liter of oxygen gas to form 2 liters of water. Let's take a look at an example problem. What volume of hydrogen gas will be produced when 5 grams of calcium reacts with excess hydrochloric acid at STP? All right, so calcium plus hydrochloric acid yields calcium chloride and hydrogen gas. We've got 5 grams of calcium. We're going to use our periodic table to go to moles of calcium. Now we can use our balanced equation to go from 1 moles of calcium to 1 moles of H2 gas. And then finally, hey, there it is, Avogadro's number. Well, Avogadro's law, 22.4 liters per mole of hydrogen. So we can factor that we would make 2.79 liters of hydrogen gas. If you've read the book The Martian, Mr. Mark Watney does calculations of this sort all the time. Next question, how many liters of chlorine will react with excess aluminum to form 7.15 grams of aluminum chloride at STP? Again, hey, it's very important that this is at STP. That 22.4 liters per mole does not work if you're not at STP. So make sure you are at STP before you go throwing around that 22.4 liters per mole. All right, as with all good stoichiometry problems, we have to balance an equation first. So 3 chlorines react with 2 aluminums to form 2 aluminum chlorides. Now we're looking for liters of chlorine, in order to get 7.15 grams of aluminum chloride. Now, step 1, we need to go from grams to moles. So we use our periodic table and we add up 1 aluminum and 3 chlorines to get the molar mass of aluminum chloride. Once we have moles of aluminum chloride, now we can go from moles of aluminum chloride to moles of chlorine. We do that with a balanced chemical equation. So that 3 comes from up here, that 2 from right there. And then finally, now that we have our gas, and that's why I included the states of matter. This only works when you're working with gases. Solids do not occupy a volume of 22.4 liters per mole. It would be a gigantic and very, very, very less than dense solid. Crunch our numbers, and we're going to have 1.8 liters of chlorine gas. Practice makes perfect. So here are some practice problems for you to work on this evening. Due tomorrow.